Okay, so what I want to do today is talk about one of my favorite subjects, the method of least squares or regression. I do this in a variety of classes, from classes on data science to probability to multivariable calculus. Whenever possible, I try to work this in because it is one of the most useful results you can learn in college in terms of how much math you need to understand it and how applicable it is to problems in the real world. And so the goal today is to talk about how can we do some data analysis? What tools do we need to do the data analysis? What can we get from it? Okay, so the first is you might know Hooke's law from physics. If you have a spring and you stretch the spring, the force is proportional to the displacement. And so here is a plot. Does this look roughly linear? Yeah. Now, this plot has something that is terrible about it. When you look at this picture, you should cringe. What is bad about this plot? No labels. So one of my favorite comic strips is XKCD. So two people are talking, and one says, I think we should break up and I can prove it. And the other is saying, I think we should give it another shot. And you see this plot of the relationship. Maybe you're right. I knew data would convince you. No. I just think I can do better than someone who doesn't label their axes. And what's nice about XKCD is if you hover your mouse over the image, you get additional jokes. The additional joke is, and if you labeled your axes, I could tell you how much better. You don't want unlabeled images. It's one of the worst sins you can do. If I'm looking at this, what if the range here is going from 1 million to 1,000,000.03? Then there's essentially no change. But I've zoomed in and I've made it look like there is a wild fluctuation. There's a whole science on how to manipulate people with how you present data. And depending on if I compress things, if I show snapshots or whatnot, I can be extremely misleading as to what's going on. So let's actually put some labels in force in newtons, displacement in meters, and at least had scales on the x and the y axis. And so here I have a hypothetical spring where the force is proportional to 5 times the displacement, y equals 5x. And I'm taking every x as every 0.2, and I'm randomly choosing things. Well, if you look at this, the span on the x-axis is about 20. The span on the y-axis is about 100. So if you do y's over 1 to estimate the slope, 100 over 20 is 5. Okay, it's looking like y is 5 times x. When I look at this, you could even say, yeah, it kind of looks like even the y-intercept might be 0, but I'm a little bit less confident about that in terms of just how it comes as I draw it down. So when we calculate the best fit line using the method of least squares, we'll get 4.99x plus 0.48. Is that close to y equals 5x? Which do you think I'm doing better on, the slope or the intercept? The slope. So we're doing a great job on the slope. 4.99 versus 5. Come on, that's absolutely fine. The intercept, not so much. Which is more important as x gets large, the slope or the intercept? The slope, because as x gets very, very large, the intercept is going to be a fixed amount, whereas the slope is going to be magnified as you increase x. So if I have to get one right, yes?
Sorry, can you let Zoe into the
So we are getting the most important one right. But our value for b for the intercept was significantly off. So I have been at over 10 institutions. When I root for football, I love the Williams football team. I love my undergraduate Yale, but my main love is Ohio State. But that's not the name of the school. What is the name of the school? The Ohio State University. In some things in life, there is a unique, there is a the. But in other things, there's more than one choice. This is using the method of least squares. If instead we use the absolute values, we would get a best fit value of A is 5.03, not bad, still very close to 5. And the best fit value of B would be less than 10 to the negative 10. 10 to the 9 is a billion. So we're talking about an error of less than 1 part in 10 billion. And so one of the big things from today is to try to decide what metric do we want to use. And depending on the metric you use, you will get different answers as to what is the best fit line. It's very similar to if you change your assumptions, if you change what you are assuming, you can get very different outputs at the end of the day. We have to be very careful about how are we choosing to measure things. Any fans of Calvin and Hobbes? Okay, so let's imagine you are going to the supermarket and we're trying to optimize. And depending on who we are, we might have different things we're trying to optimize. What do you think a parent might try to optimize as they go shopping? Cost. What do you think Calvin from Calvin and Hobbes might try to optimize? Do you want to think of his breakfast choices? Candy, taste, sugarness. Anybody know what Calvin eats for breakfast? Chocolate frosted sugar bombs, if I'm remembering it correctly. That's the breakfast cereal of choice. This is not something a parent is going to choose. Depending on who is making the optimization choice, you will fill up that shopping cart very differently. Depending on how we choose to measure error, we can actually get different best fit lines. So we talk about the best fit line. It's the best fit line given a choice of error. Okay. And so the difference is going to come from the different ways of choosing how we decide to weight the errors. So I'm going to talk a little bit about linear regression right now. At first, it's going to seem extremely specialized. It's only going to work for straight lines. Most things in the world are not given by a straight line. Well, we'll do what we can, and then we'll see, maybe can we push it a little further. So the idea is to try to find the best fit values of A and B for a hypothesized linear relationship between Y and X. So we believe Y equals AX plus B. So if we observe XI, we would predict that YI should be AXI plus B. In practice, it's almost never going to be exactly that. And we want to figure out how can we find the A and the B that will make the line as close as possible. So all the details of these calculations are in the notes that I will post. Here are three possible candidates. The first is I take the observed YI and I subtract the predicted. The second is I take the observed minus the predicted, but I take the absolute value. And in the third, I do the observed minus the predicted, but I take the square. So of the three choices, one is just right out, should not be done. Which one should not be done? The first one. Why is the first one such a horrible choice? Yes, positive and negative errors can cancel. Imagine you have a data point at the bottom left and another data point at the top right. What is the best fit line going from bottom left to top right? The line going from bottom left to top right. I, however, say the best fit line starts at the top left and goes down to the bottom right. And the reason is the errors of the two sides are going to perfectly cancel, and that will also have zero error. So if we have the first expression, the errors are signed and positive and negative errors can cancel. So the first is just right out. It now comes down to the second versus the third. They are both compelling candidates. And we've already seen that the absolute value gave a much better fit for the slope-intercept than the squares, which just gave a good fit for the slope but not for the intercept. Can anybody tell me why we might prefer the squares over the absolute value? So the third weights large errors more. Maybe that's bad. What this is saying is if you have one bad observation, and when I was an undergraduate, I participated in some psychology experiments. I did so in grad school for money. They sometimes had to throw me out of the data. And I will talk about why when the camera is not recording. One bad data point can have an incredible impact on something like this. If you have one error of 2 and 2 errors of 0, and that's a total error of 4 in the second one. If you had 2 errors of 1 and an error of 0, there would only be an error of 1. So one bad point can have a much greater impact on what's going on. So that might actually even be an argument for the second one over the third. There is a reason why we like squares over absolute values. So what class is this? I'm giving this lecture today in multivariable calculus Calc 3. What must you have taken to get to Calc 3? Calc 1 and Calc 2. So this is your third calculus class. That means you've spent a lot of time learning things about derivatives. And so the third one is great because the square function is differentiable, the absolute value function is not. So with all those calculus classes, we actually really only need Calc 1. We'll use a little bit of Calc 3, but it's really just Calc 1. The absolute value function is not differentiable. So continuing, what do we learn? Well, in Calc 3, we say a function is going to have a maximum or minimum. Where can we find that? Well, the candidate points are going to be the places where the derivatives vanish. So I would take the partial derivatives of the error function with respect to a and b. This is just generalizing what we did in Calc 1, where if we only have one variable, it would be f prime is 0. And after a little bit of algebra, we get an expression for the best fit parameters, a hat, b hat, or I can write it out in long form down below. This is very similar to the quadratic formula. Is the quadratic formula great? Yes. And the reason is no thought is required to solve a quadratic. As long as I tell you ax squared plus bx plus c, if I give you a, b, and c, you feed it into the quadratic formula and it gives you the answer. Now, if the polynomial is nice, you might say, well, rather than doing a, b, c in quadratic formula, I might try to see if I can just visually factor it and solve it like that. And that's more of an art form. And if you can do that, that's wonderful. But if you can't, you at least can fall back on the quadratic formula and solve it that way. Here is an explicit formula for the best fit parameters a and b. If you use the absolute value, we don't have explicit formulas. You have to do numerical techniques to find them. So this is wonderful. I can write down best fit answers immediately. And this just means, summing little n goes from 1 to capital N. So it'd be x1, y1 plus x2, y2 plus x3, y3, and so on. When you see these answers for a and b, what's the one thing that worries you? What's the one thing that worries you about these expressions? Yeah, what if the denominator is 0? It turns out the only way the denominator is 0 is if you are a complete and utter moron. There's no other way to phrase it. You have to be truly stupid to be in a situation where the denominator is 0. And let me explain what I mean. Imagine you believe that the time it takes a ball to roll down an inclined plane depends on the angle, depends on the incline. And so you decide you're going to test and try to figure out how the time depends on the angle. And what you do is you take a plane with an angle of 30 degrees and you roll the ball. And then you take the same plane with 30 degrees and you roll the ball again, and then again at 30 degrees, and then again at 30 degrees, then again at 30 degrees, and once more at 30 degrees. And using only data with an angle of 30 degrees, you are now going to try to predict what will happen at other angles. Should you be able to say anything about the angular dependence if you're always measuring it at the same angle? No. That's the only time this formula breaks down. It only breaks down if all the x's are the same. Imagine every x is 4. Then this is 4 times 4. I can pull those 4s outside the equation. And this is just the sum of 1 times 16. If x is 4 every single time, and I have a 16 here, the sum of 1, the sum of 1. If all the x's are the same, the denominator is 0. It turns out that with a little bit of more work, a little bit of algebra, you can show that if the x's are not the same, then it is not always going to be 0. And so to try to show this, I am going to try to show the impossible Rubik's Cube. So if you hold it just right over here, all the pieces on the side look green. But if I shift it a little bit, now they become multicolored. And so it's a great example of the power of looking at things the right way. If you look at something just the right way, you can often see the relationship. And if you look at it the wrong way, you're going to just be pulling your hair out. And we have to figure out what is the right way to look at this. All right. So let me talk a little bit about the theory. And it's okay if you don't follow all of this. This is just trying to highlight how you would attack a problem like this what goes in, give you some motivation for other classes like linear algebra down the road. So remember, X and Y are not the variables. X and Y are what we're observing. It's the A and the B that are the free parameters. So our error is a function of A and B. And the goal is to find the values of A and B that make the error as small as possible. And so in one variable calculus, the candidates for the maximum and the minima are places where the first derivative vanishes, the critical points, and then the boundary points. And so we do something similar here. And so here, because we have two variables, we want the partial derivative in each direction to be 0, or we have to be on a boundary. Well, A and B can go off to plus or minus infinity. And if you think about it, if you take A and B very, very large, you can make the error tremendous. So we know the error is not going to come from A and B going off to infinity. That's not going to give us the smallest error. The smallest error is going to come from some reasonably sized choices for A and B. So we need to calculate the derivative of E with respect to A, the derivative of E with respect to B, set them both equal to 0, and solve. Okay? So if we take the derivative with respect to A, again, xi and yi, these are fixed numbers. So we have the power rule. So the 2 comes down, then it's yn minus axn plus b to the power 2 minus 1 to the first power. And then we take the derivative of the inside piece with respect to A, and that just gives us negative xn. And similarly for the second one, when we take the derivative with respect to b, we'll get negative 1. We set both of these equal to 0, so we can divide both sides by negative 2, and we get the following expressions. So it may look complicated because we have all these sums, but it's really 2 equations and 2 unknowns. What are the 2 unknowns? A and B. And so this piece over here, the sum n goes from 1 to big N of yn times xn. There'll be y1 x1 plus y2 x2 plus y3 x3. Then we have the sum hitting negative ax and xn. You can pull out the a and you'll get x1 squared plus x2 squared plus x3 squared. And so when the dust settles on the algebra, I can write it as the sum of the xn squareds times a plus the sum of the xn's times b equals the sum of the x and yn's. And then similarly for the second line, 2 equations and 2 unknowns. If you're comfortable with matrices, I can write this in matrix form. And then if this matrix is invertible, if I apply the inverse of the matrix to both sides, I then solve for the values of A and B. And so for a 2 by 2 matrix, the formula for the inverse of the matrix is 1 over the determinant alpha delta minus beta gamma, and then I just flip some of the entries and put in some minus signs. So as long as the determinant is not 0, the matrix is invertible. All right, well, let's look at our matrix. So what's the determinant? It's going to be upper left, bottom right. That multiply those together and then subtract the diagonal, the product of the diagonals. So we want to show that this is not 0 if the x is varied. And again, that's why we're showing the Rubik's Cube today, the power of perspective. Can you look at things the right way? So let's define the mean x bar as the average value. It's the sum of all the x's divided by n. So if you have an exam, you take all the exam scores and divide by the number of students in the class, and that will give you the average score in the exam. It turns out by doing some algebra, which I encourage you to do, you can show that the determinant is just some nice multiples of the number of data points times the sum of xn minus x bar squared. Well, now that we have it written like this, it's actually a lot easier to analyze. If all the x's are the same, well then xn has to be x bar if they're all the same. If every value is the same, that's the mean, that's the average value. And then the determinant is 0. If they're not all the same, at least one of them can't be the mean. In fact, you can say it more than just at least one, at least. If at least one of them is not the mean, how many do you know can't be the mean? No, I'm sorry, 2. If everything was the mean but 1, if the mean was 5 and everything was 5 and one of them was 7, then the mean can't be 5, the mean would be a little bit more. So if one of them is a little bit above the mean, at least one of them is a little bit below the mean. So we know that there has to be at least 2 things that are not the mean. And so when we look at these sums of squares, we know that can't be 0. And interestingly, expressing polynomials like this is one of the mathematical ingredients in some of the approaches to having computers drive cars, in terms of coming up with evaluation functions so that the car hopefully doesn't hit things. is expressing certain things as sums of squares to do some of these calculations. If we look at it the right way, we know as long as we vary the x's, we're going to be in great shape. All right, so now there's a lot of different ways we can write the best fit values. Depending on how you want to write things, you can write it this way by using x bar and sigma x squared, the average value of the x's, and essentially the standard deviation of the x's. If you want to do it like that, absolutely fine. If you want to do it this way, absolutely fine as well. There's lots of different ways to express these formulas. I like this formula. This is actually particularly nice. I can substitute what the different sums are. You could have an Excel or Google sheet where you put in the x's and then just sum things and just plug it in. It is wonderful. It's explicit, it's fast. Now, whenever you have an answer, you always want to check and see, is it reasonable? So let's imagine we have y equals ax plus b, and if y is in seconds and x is in meters, well, if y is in seconds, then b has to be in seconds. So if y is in seconds, b is in seconds. If x is in meters, a has to be in seconds per meter. And you can go back over here and you can check and see, does this give the right answer for a and b for their units? It's not a proof that you haven't made a mistake, but it's a really nice consistency check. If I plug in the units for x and y, do I get the correct units for a and b? Okay. There's other ways to do the calculation. So imagine when the dust settles, we had 4 is 3a plus 2b, and 5 is 2a plus 5b. Well, one way we could solve this is I could solve for b in terms of a. So 4 minus 3a is 2b, 4 minus 3a over 2 is b, and substitute that in here. Now I have one equation for a, I solve for a, then I plug that into the other one and I get b. Another way is I could say, well, if I multiply the top by 5 and the bottom by 2, they now both have 10 copies of b. And now if I subtract, the b's cancel, and I get 10 equals 11a, or a equals 10 11. How much calculus have we done in this problem? Just a little bit. We just did a small amount of calculus to take the partial derivatives, and then everything else was algebra. This is how a lot of advanced mathematics is. The amount of the advanced math that you use is very small. Most of it comes down to algebra and trying to write things in good ways. And then there's often many different ways to do the algebra. You can do it with matrices, you can do it by substitution, you can do it by taking combinations of the equations. Any of these are fine. All right, so extensions. So if we could only use this for linear relations, it would be extremely restrictive. So we want to show that this actually holds in much greater generality. So we did y equals ax plus b. It turns out that all that really matters is that it's linear not in the variable x, but it's linear in the unknown parameters. So if I had a combination of functions, if I had some multiple of the function f1 and some multiple of f2 and some multiple of fk, maybe the first one is x cubed, then x squared, then x to the first, then 1. So I'm trying to find the best fit cubic. The exact same theory would apply to find the best fit cubic. Or maybe I'm trying to write it as a copy of some multiples of sines and cosines. As long as it's linear in those, the same method would work. For the best fit line, we had a 2 by 2 matrix. If I did the best fit parabola, what size matrix do you think we would have? So for a line, we had the parameters a and b, we had a 2 by 2 matrix. For the best fit parabola, we have a, b, c, ax squared plus bx plus c. What size matrix would we have? 3 by 3. And so the matrix just becomes a little bit more involved. The algebra becomes maybe a little bit harder, but fundamentally it's the same idea. And so we can generalize this very nicely. But if instead I said y equaled x to the a, where a is the exponent, now we can't do it. So if we wanted to take the derivative of x to the a, well, x to the a is e to the a log x, and a is the variable. So when you take the derivative, you would get the log of x times e to the a log x, or you'd get the log of x times x to the a. A would still be in the exponent, and we would not be able to solve it using just basic linear algebra, using basic algebra. It's only because it was linear here, and we were squaring things, that we ended up with a to the first power, b to the first power, and we could solve. So we can't solve if it's an exponent. So if we have something like Newton's law of gravity, the force is proportional to the product of the masses divided by the square of the distance, we're in trouble. Well, let's imagine we didn't know that it was a 1 over r squared force. Let's imagine we thought it was proportional to the radius to some power a. How could we figure out what that power a is? Well, hopefully in your high school classes, you've seen logarithms. Did you ever see anybody tell you why we care about logarithms other than we can work with large numbers? Here, finally, is an application of logarithms. If we take the logs, we get the log of f is a log r plus little b. Oh, okay. The role of y is going to be played by log of f, and the role of x is going to be played by log of r. It's y equals ax plus b. It's now a linear relationship. And so what was initially nonlinear, was initially a power law, has become linear, and now we can use the method of least squares. We can now use regression. And that is why, even though it looked very, very specific before, tailored just for straight lines, it's actually not that big of a constraint because so many things can be linearized. So let's see a couple of examples. Here are 25 of the most populous cities. I think these are American from a few years ago. I really don't see that much when I look at a table like this. If I plot it, I can plot the rank of the city versus its population. Can anybody tell me what curve that is? I can't either. But let's do some transformations of the data. I'm going to plot the rank versus the log of the population. This is often known as a semi-log plot. I've taken the log of one of the items. I still can't really tell what that is. But if I plot the log of the rank versus the log of the population, that actually looks pretty linear. Now here's a plot of the 100 most populous cities. And when we do a log-log plot, you can see a straight line does a phenomenal job of describing the behavior. Here is a plot of rank versus occurrences for word counts. And you, again, no idea what form that is. But if I do a log-log plot, it's not perfectly linear, but there is definitely a good general linear trend in what's going on. All right, so what I want to do is I want to talk about two applications, one from my personal life, chapter 78, the other from physics or astrophysics, Kepler's laws. So this was a real world challenge. So a couple of years ago, Williamstown and Lanesboro were regionalized. So the two towns had been sharing a middle high school for 50 years roughly, and they had each town running an elementary school. So there was one school district in Williamstown for Williamstown Elementary, one school district in Lanesboro for Lanesboro Elementary, and then there was another school district for the Mount Greylock Regional School, which was the middle high school. How many school committees do you think we needed for 3 schools in 3 districts? No, that was the whole point of regionalizing, is to get down to one committee. We had 3 different school districts. So how many school committees did you need? Actually, we had 4. Each school had their own committee, and then we had a super committee, it might have even been 5, depending on how you're counting, where the 2 elementary schools sent people up to a super committee, and then the middle high school sent somebody else to that 2 people up to that super committee, and you had 4 people drawn from the, it was a logistic nightmare. The number of times our senior administrators had to go to essentially the same meeting at 3 different schools. All right, now let's talk about the policy. So it's not going to be okay to hit somebody in one school and not another. This is pretty standard in terms of most of these things are going to be the same. It was not a good use of time. There were a lot of positions that could be shared across the districts if we could regionalize. One of the things we wanted to control was how each town ran the elementary school as much as possible. We wanted the towns to have control as much as possible over the finances of their elementary school. Now the budget is about 21 million. We got about 3.5 million from the Commonwealth of Massachusetts in Chapter 70 funds. Before regionalization, we knew how much money went to each school. But the way it works is they only tell you how much money goes to each school district. Well, if your school district has just one school, school and district are essentially the same. But if you now have 3 schools, they would now only tell us how much money goes to the district. And we needed to figure out how to allocate the money between the 3 buildings. The state had a formula with a lot of variables to calculate this, but they kept it secret. But we had years of data. And so the question was, could we try to figure out what their formula is? So this is a great example of why you want something like linear regression with the method of least squares. Given some parameters and some data over time, can you predict how things might be in the future? Can you predict how new values would be? And so the objectives, when I was trying to come up with the formula, is I wanted a fair formula that did a great job predicting. I wanted it to be transparent, that people would agree is fair. And I wanted something that I could explain to the select boards, to the finance committees, and to the voters. Could I do a better formula if I had 16 variables and some freedom to choose things? Possibly. And you can imagine the nightmare that this would be to try to explain, as well as the fights you might then get as to, well, why did you peg that value of your parameter as this as opposed to that? This is very clear. And so by using the method of least squares of linear regression, we actually got a really nice formula, and we only used essentially two ingredients: the populations of Lanesboro Elementary School, less Williamstown Elementary School, and Mount Greylock, the middle high school, and then what's called the EQV, basically the town assessments, the value of the property in the two towns, as just some way of considering how much the two towns are worth. So what properties do we want the solution to have? Well, we want the solution to exist. We want the values that we assign to the schools to be between 0 and 1. We want it to be stable under small changes. If one more person is added to one of the schools, you shouldn't see a 5% swing in how much money is being allocated. And you want the sum of the percentages to add up to 1. Some of these are not a big deal. If the sum of the percentages doesn't add up to 1, well, if it adds up to 1.03, then you can just rescale everything by dividing the amounts by 1.03. So it's not a big deal. It turns out that it does add up to 1. It is stable under small changes. It may not be stable under large changes. We did some calculations. If 40% of the kids die and 60% of the buildings burn down, you may no longer be able to trust the results. However, if 40% of the kids are dead and 60% of the buildings have burned down, this is the apocalypse. This is even worse than what we have going on right now in the COVID pandemic. And we have bigger problems than whether or not this formula is working. And so in small changes, we do have stability. And so here's a little bit of a plot of what's going on for the data I had going up to 2018. And you can see that there really isn't that much change in the percentages over the years. There's some, but there's not wild fluctuations. And so what I did is I actually predicted what 2018 should be before we had 2018 values from the state, because we hadn't regionalized yet. And so I predicted the percentages for the different schools. This was the predicted, this was the actual, and this is how much I was off by. So I was off by at most around a little bit less than 0.3%. To put things in perspective, of $3.5 million, 1% is about $35,000, 0.3% is about $10,000. So, and how to allocate 3.5 million, we're missing by on the order of $10,000 per building. $10,000 is not nothing, but it's a small amount relative to the 1.5 million. This shows you how powerful the method is. And the regional agreement the two towns did regionalize now actually has annually a linear regression that has to be done to allocate the money. Okay, so as we've mentioned before, a lot of relationships are nonlinear. If I have y equals bx to the a, if we take logarithms, we can linearize things. So one of my favorite examples is Kepler's third law. The first law is planets travel in elliptical orbits with the sun at one of the foci. The second is they sweep out equal area and equal time. And the third is the square of the period, how long it takes to go around the sun, is proportional to the cube of the semi-major axis. Now this is how the hell do you discover this empirically? So imagine we didn't know this law. We thought that there was some relationship between the period and the semi-major axis. Could we discover this through statistics? Well, rather than doing t squared is L cubed, you should be aware that something's going on because I chose my variable to be b tilde. Normally you don't put a tilde on something. If I take the square root of both sides, I'll call the square root of b tilde b, and I get the period is just b L to the 1.5. You might as well assume that the power of t is 1 and then just adjust the power of L accordingly. So the question is, could we figure out that t is proportional to some power of L? So what I'm going to do is I'm going to give you the data, and you can do this as a homework problem, for the semi-major axes of the planets. When I was a kid, I would have had to give you 9 pieces of data. Now I only have to give you 8. And I will use astronomical units. One astronomical unit is the distance essentially from the Earth to the sun. And for the time, I will use the orbit in period, the orbital period in years. And when you look at t equals BL to the A, any thoughts about what B should be using this data in these units? Any planet you particularly like? Earth. So let's highlight Earth. The length of the semi-major axis of Earth is 1, and its orbital period is essentially 1. What should L be? I mean, what should B be? If when t equals 1 and L equals 1, what will B be? 1. This is why I chose these units. In these units, things are very nice. Yeah. There's a lot of fun units in the world. I urge you to look up the Bruno, the Millie Helen, the Slug, and the Smoot. I will talk a little bit about the Smoot. It's one of my favorite stories. This is the plot you will get when you do the homework problem, and you will see a terrific, terrific fit. Yeah, absolutely amazing. All right. This is one of the bridges in the greater Boston area. It's about 620.1 meters, but there is another unit for it. Does anybody know the other unit for this bridge? It is 364.1 smoots plus or minus an year. So Smoot was an undergraduate at MIT, and he was pledging a fraternity. And the fraternity was curious. How many times would they have to pick up Smoot, put him down, pick him up, put him down to cover the entire bridge? And fortunately, they were able to do this, and they were able to solve the science. It's 364.1 times plus or minus an year. And they put down a little chalk marking or something like that every time they put him down. Well, the police in Cambridge, the city, was not thrilled, so they cleaned it up. The fraternity was not thrilled, so they did it again. And eventually, people just got fed up with cleaning it up, and they just left the Smoot marks in. It's now become completely institutionalized. And they now have official Smoot markings on the bridge. So when there is an accident, they report how many Smoots from the end of the bridge did the accident happen. Anybody know whatever happened to Smoot? You can't make this stuff up. Seize opportunities in life. You never know where they will lead. Oliver Smoot, chairman of the American National Standards Institute from 2001 to 2002, president of the International Organization for Standardization, 2003 to 2004. I'm just trying to imagine the application. I don't want to brag. I am a unit of measurement. And this is something that could have easily been a very embarrassing, or it's something you can roll with and have a good sense of humor. And it becomes an interesting story. When you are trying to connect with people, you want to find ways. One of my favorite winter study classes I ever taught at Williams was a class on cryptography. And I encrypted the title. And the registrar's office asked me, are you sure you want as the title of your course? Absolutely. When my students are applying for jobs, it's going to be a conversational starter. And several students came back and said, you were right, Professor Miller. I was asked, what is this on your transcript? All right.